Esto está como transmitido en línea. En línea.
All over the world.
All over the world. Ah, qué top.
¿Presentar en español?
No sé, como queráis.
Yo pero inglés, pero...
O sea, no sé, como que es medio raro nomás presentar en inglés cuando hay pura gente que habla español, pero como queráis me da lo mismo. De hecho, hay una slide al principio que están en español, pero después la parte técnica en inglés, como quieran.
Your choice. José. So we're very happy to have José Verschae, Director of the Engineering and Science Universidad of Higgins. So thanks for coming, José.
Okay, thanks a lot for the invitation. So today I'm going to give a talk on the latest stuff that I've been working on. And at least part of what I'm presenting is together with Matias Villagra, who is my student that I had from Catholic University when I was there. So Eduardo asked me to give a few slides about myself. So I'm going to present very shortly my CV. So I took a degree on mathematical engineering I graduated at 2008 from the University of Chile. Then I did my PhD at the Technical University in Berlin within the Berlin Mathematical School, which is a joint program in Berlin between 3 different universities. Then I did a postdoc at the Universidad de Chile for a couple of years. Then I was hired as an assistant professor at the Universidad Católica, and a few years ago I was offered a position at the newly funded university in Rancagua, Universidad de O'Higgins, which is a public university created only 3 years ago. And there I'm the director of the Engineering Science Institute, as DIIIO mentioned. So, yeah, so this is kind of strange to say this type of thing in a seminar talk, but anyhow. So, okay, I mean, I think that I just put a few highlights of my CV, but I think that I'm a very active part of the community, even in Chile and in my research area in the world. I have a lot of collaborators from many universities in the world. I have like an active way of working, such to always increase my network. I participated in several projects. I have had 3 Fondesit projects. I've been part of a Núcleo Milenio. I've done a lot of referees for journals, conferences, and projects, and I've been organizing lots of workshops and summer schools, and also been part of program committees of different conferences, international conferences. Okay, so that was just very brief about myself. And then what my research area is combinatorial optimization, okay? So optimization problems in which you have to take discrete decisions at the end of the day. And the main point there is to design algorithms for solving those problems, right? And then one particular problem that I've been working on for a long time is a scheduling problem. It's actually a load balancing problem, what it's called, which is very easy to describe, and I like it a lot because it has a certain simplicity on it. But then the idea here is always to design better and better algorithms. It's a very classical problem in the literature of operation research. And it's called the minimum makespan problem. So you have, in particular, you have n jobs. Let's say each of these boxes represents a job. And each job has a processing length, which is just the length of this little rectangle here. And you have a bunch of machines in which you need to assign the jobs to the machines. And this picture here is like a Gantt chart, right? Just assigning jobs to the machines. You will need to design the time slots, but for this problem it's not really important. And the idea is to balance the tasks among the machines in a fair way. And there's many ways of defining that. One way is to say that you look at the load in each machine. The load is just the sum of the processing times. And this defines a makespan, which is the maximum load, and you try to minimize that. So in this very simple example, that's the optimal solution. And it's not the unique one. You could, for example, put this job in that machine and nothing would change. Yeah? Okay, so like from a computational complexity point of view, this problem is hard to solve. So there is no efficient algorithm for this. And unless P equals to NP, so the problem is NP hard. And then you try to find the best possible solutions for this that allows in polynomial time. So one way of doing that is that you look at a formulation, an integer programming formulation that might look like this. For example, you might have, this is like the most standard simple way of formulating the problem. You have a variable xij for each job and for each machine. And this variable will be 1 if you assign the job to the machine and 0 if it's not. And then you add a bunch of inequalities to say that this solution is feasible. So this says, for example, that every job has to be assigned to exactly one machine. This one says that T is the makespan, so it's the value of your optimal solution, which is what you're trying to minimize. And then you have a bunch of inequalities, for example, to say that the makespan, so you try to push this as much as possible to the left. So T will be equal to the maximum of this value. This is exactly the load of the machines. And then you have a few other, like for example, this is not really important. Okay, and then you have a variable that's either 0 or 1. But then the problem is NP hard, so what you do usually is you relax. Okay, you relax the conditions to get a linear programming formulation, and then you have a variable that is between the interval 0 or 1. Okay, and then you ask, okay, how much of a mistake I did by relaxing this condition? This is one of the main questions. And for that, you look at what is called the integrality gap. So you look at the problem in a more somehow geometric way. If you think about it, you have a bunch of linear inequalities. So this defines a polytope, which is, for example, this polytope over here. And you're interested in the integer points within that polytope. Yeah? And then you ask yourself, okay, the real problem that I'm looking for is optimizing some linear function, maybe it's in this direction or something like that. And the optimal solution, the real optimal solution when you're looking for an integral solution might be this one. But when you relaxed, you got some different optimal. And the question is how much of a difference there is in the objective function of these two problems, right? And this is called the integrality gap. And the integrality gap is defined as the ratio between these two values. Yeah, and you want to have this ratio as close to 1 as possible. This is one way of thinking about it. Okay, so for this formulation right here, this ratio, if you look at the worst case over all possible instances, can be rather large. Can be like a factor of 2 away. And this is not very satisfying, right? Like you would like to have something much closer. And there are other formulations that have a slightly smaller integrality gaps, but there is always a gap. There is always something that you cannot really get as close to the optimum as you would like. So what we were trying to do, we were trying to get somehow, in some sense, these two polytopes as much as close as possible. And there's one or two relatively new techniques that is very hype in the literature to try to get this, which is called the hierarchies. Okay, so there are two very famous hierarchies that appear, well, one in the 90s and the second one appeared in the 2000, like 20 years ago. This appeared in the literature, and then maybe like 10 years ago, this started to be used quite a lot in the area. And the idea is very simple. So like you have this big polytope is your original relaxation, and then you try to come up with relaxations that get tighter and tighter. Yeah, and you do this through these hierarchies. So these hierarchies does this somehow automatically. You don't need to think too much. You just apply this thing, and you get nicer, tighter and tighter relaxations. Okay, so very, very short said in a nutshell, we can. So this sounds very nice in the sense that you don't need to think. You just apply this thing and get better and better relaxations. If you get if you go through these steps long enough, you eventually get the real polytope that you're looking for, which is the convex hull of the integer points. But the problem is that the complexity of these polytopes increases too fast. Okay, so pretty much if you go through only a constant number of steps, you can deal with these polytopes, meaning that you can separate them in polynomial time. But if you go further, things get too complicated. So this really doesn't work. Okay, and there are two of these hierarchies. One is called the sum of squares hierarchy. And this has the disadvantage. I mean, this is, okay, there's the sum of squares and Sherali-Adams. Sum of squares is always stronger than Sherali-Adams, so it gives you better relaxations at the same level. But has the disadvantage that the relaxation is a convex relaxation. It's a semi-definite program relaxation, while the simpler Sherali-Adams one gives you a real polytope. It's a linear relaxation. Okay, so what we proved is the following. This is not the real result that I want to talk about. This is just like the motivating what I'm talking about later. And what we show is that for the stronger hierarchy, even if you go in a lot of these rounds, in a lot of these levels, like linearly many, you still have some small but constant integrality gap. So you cannot get as close as you want. There's no trade-off in which you can pay for having more hierarchies, like constantly many levels if you want, and decrease the integrality gap to something that you can control. So this is like a very negative result. And one thing that you notice in the literature when you see this type of results is that there seems to be the fact that there's a lot of symmetries in the problem is the issue with this. So symmetries, I mean, for example, here I have all the machines that are identical. And if I have a solution, I can permute the machines and I get another solution. So that's what I mean with symmetries. And so we thought, like, okay, maybe if we understand a little bit better what the symmetries means or how we can deal with them, we can get around this very bad result. And this is exactly what we did. And the de facto way of dealing with symmetries in the literature, like if you talk with anybody that does integer programming and you have a symmetry problem, the first thing you try to do is just to break symmetries. So this means just add a bunch of inequalities that destroy the symmetries. And this is exactly what we did. So we took this LP, we intersected with some symmetry breaking constraints, and then we got this trade-off we wanted. Okay, so you can get, you choose an epsilon, positive number, small, and then you can get a 1 plus epsilon integrality gap, so you can get as close as you want to your polytope, and you only have to pay a constant number of rounds. So you get this trade-off, which is not possible if you don't round, if you don't break the symmetries before. Okay, so one thing that it was very unsatisfying, if you think, in some way, was that the way in which you break the symmetries, like the exact inequalities you had, were like very sensitive to whether this thing worked or not. So if you had some type of symmetry breaking inequalities, things work nicely, but if you change them a little bit, the techniques were breaking completely. And I'm not going to get into the details of how we did that, but that made us thinking, like, okay, so why? Why is one way of breaking symmetries better than another one? Especially because symmetry breaking techniques is something that people use all the time in integer programming. It's like very natural to add symmetry breaking inequalities, but it was very unclear why one way was better than the other. And we thought that it was a very fundamental question in the theory of integer programming. Nobody was looking at this question. So this is kind of a motivation for what I wanted to look at afterwards. And if I just want to kind of state the main idea of what we are trying to do is the following. So imagine you have a polytope. This is a polytope in 3D. And you look at it, and just in an intuitive way, this polytope has lots of symmetries, right? So if you take this polytope and you reflect it around some hyperplane like that, then you get the same thing. If you take it and you rotate it by some degree, you get again the same polytope, and that's symmetries of the polytope, right? Okay, so if you want to describe this polytope, compactly if you want. So it's very natural to say, now you know what, instead of describing this full polytope in which you have plenty of facets of these inequalities like this that are essentially just rotations of another. Like this facet here is just a rotation of this facet here, and it's just the same thing as that one, just rotated many times. So it makes sense to just look at one piece of this polytope, like for example that one, and say, you know what, if I want to describe this polytope, I will just describe this one, and the rest I will just get it by these rotations, right? So I can just take this piece and rotate it by 90 degrees 3 times, and then I just reflect it again, and then I get the full polytope again. It's just because there's a lot of redundancy here, right? Okay, so this is pretty much when what happens when you're dealing with symmetry breaking. So you have this very symmetric object, you intersect it with some set, and you get something that looks like that. And then, yeah.
Is there a technique to identify the symmetry?
Yeah, I will get into all of this. Okay, I'm pretty much just motivating what I'm talking about later. Okay, so by the way, what I'm talking about is joint work with Matthias and with a postdoc, Leonard, and it's still work in progress. Yeah, so we're not done yet. But I'm very excited about this stuff. That's what I wanted to talk about it. Okay, so what are symmetries? So first of all, what is a symmetry? So how do you formally define it? And then how you actually deal with this, either algorithmically or mathematically, like both are. Okay, and symmetries is, at the end of the day, is group theory. So group theory is symmetries, and symmetries are group theory. Okay, but we're dealing with very simple type of symmetries, or very specific type of symmetries, which we call permutations. Yeah, it's just permutations. So essentially, we're just permuting variables. So the intuition behind it is that you have an integer program, and then whenever you have a solution, you can permute the variables in some way. And if you get another feasible solution, then this is a symmetry. This is kind of the intuition. Okay, I will get to that a bit in a few slides. But we're dealing with permutation groups, and permutation groups is the following. So let's look at, you have, let's say, the natural numbers from 1 to n, and you're looking at permutations. So that means that you have functions from this set to that set, which are invertible functions. So this is called the full symmetry group, Sn. And what you're looking at is a subset of these permutations, which is closed under compositions. Okay, and that is called a permutation group. Okay, so for example, you can have, this is a permutation, this is a notation for a permutation. This permutation means that you send the 1 to 2, 2 to 1, 3 to 4, and 4 to 3, yeah, and so forth. And you look at, for example, and the group G, which is this notation means that this group is generated by these two permutations, and generating means that it's the smallest group that contains these two guys. Okay. A few things about it. This is very relevant for what we're going to do. Is that whenever you have a group, so the number of elements in the group can be really big, because Sn has n factorial many elements, right? The number of permutations on n numbers is n factorial. So the group can be humongous. You cannot just write it out in your computer. This will be too big. So the way you describe a group is usually by giving a set of generators. So this means that you just give like a small number of elements, and then you say that you are dealing with the group that is generated by those elements. So the smallest subgroup that you can get by essentially taking compositions of these guys. And there's this result by Baba in the 86 that says that if you take any generator that is minimal, you get at most 2n elements. So this is very, very important, because you might have a group that is huge, but you can always describe it in a compact way, just by listing 2n many permutations. Okay, and then what we consider is what is called an action of the group on Rn, which is just permuting the variables. Okay, you take any permutation, and we write a permutation sigma in some group, and then you write sigma x, which is x in which you permute the variables by this permutation sigma. Yeah, This is called an action, blah, blah, blah. That doesn't really matter. Okay, so now let's get to an optimization problem. So let's say you have a problem in which you're minimizing some given objective function, subject to a variable that is in a subset K. Now, we say that this problem is G invariant for G is some permutation group if two things happens. So, and I think that it's very nice to have this picture in mind. So if you take any, so here, this problem here that I'm describing here, so you have this polytope, this is K, you have this objective function which you are minimizing some linear thing, and then this thing is invariant under the group that swaps the two variables. This is rather natural, I hope. And what you need is that if you take any point, for example, this one here, this is X, and when you permute the two variables, you get some point over here, so you're reflecting against this line, and then you get another point which is also within the polytope, right? So this is one thing. So if X is in K and sigma is in your permutation group, then sigma X is in K. And then the other thing is that whenever you take X and you take sigma of X, you get the same objective function, right? Okay. So therefore, this is a very simple example. You're summing over all xi's such that xi is larger or equal than epsilon. Now, if you permute the variables in any way, and you have a feasible solution, you get another feasible solution, right? Like this is obviously a toy example, but just to get the point. And this is an invariant for the whole group of permutations. But it could be, so for all the programs, you are invariant only for a subgroup. Okay. So what we're looking for is somehow the idea is that there is a lot of redundancy in the description of the problem, and then you don't need to describe the full thing. And somehow in this very simple example, if you want to describe this full polytope, you just need to describe the upper part and then say that you reflect the rest. That's the idea. Okay, and that object is called a fundamental domain. So a closed set F, we say that is a fundamental domain for the group if there are two things that happens. First of all, if you start applying the permutations of the group to F, for example, you take, in this case, a fundamental domain is just this semi-space up there in drawing, and then you apply one of the elements in the group, which is just reflecting this guy over this line. And then this is covering the full space. This is covering Rn. And the other thing that you, maybe, is there like a marker somewhere? There are plenty. Yeah. Thanks. Okay, and the other thing that you kind of would like that is that the description is somehow unique. So you would like that this holds. So if you intersect F with sigma F, so in this case, you have this semi-space, it's a closed semi-space, then you intersect it with sigma of that, which is this other semi-space on the other side, and you would like that the intersection there would be empty, because hopefully kind of there is no redundancy on the description of every point. That's the idea. But obviously there is a problem here in the boundary, so you require that only for the interior of the sets. That's the idea. Yeah. Okay. Otherwise, you're kind of lost. Okay. So that's formally this is a symmetry break. This is symmetry breaking. So you intersect. You have a problem. You have symmetries. You intersect with some inequalities that describe a set like this, and this is breaking symmetries. So people usually don't think about it that way. Okay, fine. But this is the way. And the first question you think of is, okay, so like, how can you construct such a set for any group, right? Okay, and there's one way that is found in the literature, which is the following. And to understand this, it's better to make a small picture, which is the following. Like, okay, take any x, any set x, and any point x in Rn, and start to look at all the symmetric points with respect to that. So that means that I apply every possible permutation in my group to x, and I start getting a bunch of different points, right? So the intuition around this idea of fundamental domains is that you would like to pick out of all of these symmetric points, you would like to pick just one of them, right? Okay, and one way of doing that is saying, okay, I will define some vector gamma, and now out of all of those points, I will pick the one that maximizes this linear function gamma. That if you start like, so in this case would be probably this guy. This guy would be the guy that maximizes. So this is called an orbit, the orbit of X. And out of all the orbits of X, you pick the one that maximizes this linear function. Okay, if you think about it this way, and nobody tells you when you read the literature, this is the way to think about it, why you're maximizing a linear function and not something else? I don't know, but in principle, you can change what you're maximizing, right? Okay. And this defines always a fundamental domain as long as gamma has pairwise distinct entries. Whatever, doesn't really matter. Okay, this sounds all good. So we have like a way of breaking symmetries that works always. But if you look at the inequalities, you have like X will be in this fundamental domain of gamma if gamma transpose X is larger or equal than gamma evaluated on any symmetric point of X, like any point in the orbit of X. But then you will have one inequality for every element in the group. And the group might be exponential size. So that's already something that you think, okay, this is not so great, or might be difficult to deal with this set. And this is actually what happens. So there's this theorem by Margot that says that separating this type of fundamental domains is NP hard. So you cannot deal with this algorithmically, which is a pain. It's not what you would like. But for some specific cases, you can. Okay, but then you think, okay, but this is just like one way of breaking symmetries. Maybe there's another way of breaking symmetries for other or like for in a different way that gives you a better or a way in which you can handle things. And a different question is like how effective this is in practice when you do algorithms with this stuff, right?
It's not enough to, for some groups, maybe is it possible to reduce to a generator?
Say again?
Can you replace G by a generator?
No, usually that doesn't work. But there's some specific classes of groups for which this works. Like, for example, groups which are just given by taking reflections, like reflection groups. This works. But this is usually not the case. And it's not clear also, it's not well classified. There's very little work on this, so quite surprisingly. So it's not clear for which groups you can handle things, for which groups are easy, which classes appears in practice in which you can actually handle them better. So that's why I think that this area and this topic is so excited, is because there's not much literature on this. Okay. So what we propose is like a different way of breaking symmetries, which is the following. So imagine, this denote the lexicographic total order in Rn. I put Rn plus, but I think you can put Rn. And I will give you an example of what this means, but this is just some total order on vectors in Rn. And you define this set, which we call lex of a group G. So I will say that this is the set of all elements, all vectors in Rn that are lexicographically bigger than all of the other elements in the orbit of X. So similar to that, to what was previously defined, it's just that we're kind of changing what is the objective function in some sense. Before we had like this linear function, and we are considering the lexicographic order. Okay, and just to give you an example, to give, say again? No, that's defined for all elements, but I will get to that. Okay, so, and this is, okay, let me give you an example first. So let's say you have, G is the cyclic group of three elements. This means that the elements in G are the ones that you have these three elements in your vector, and what you can do with this group is to shift them in circles. right? So you can get from this to this vector over here by shifting all elements down, and the last one you put it in the first coordinate, right? Okay, so if you look at this vector over here, what you see is that this guy is lexicographically bigger than that guy. Why? How do you define this thing? You look at the first coordinate in which these two vectors differ, and they already differ in the first coordinate, and this guy is bigger than that one. So lexicographic order is the same as you do in the dictionary, right? Yeah. And then you see that this guy is in lex of G, for this G, right? We didn't put the G. And this one, then, and therefore this one is not, because these two guys are in the same orbit, but this guy is lexicographically maximal than that one, right? Okay. And so what you can prove, and I'm not going to prove this, and it takes a little bit of effort, it's not completely direct, is that this set is convex. It is not obvious. It's not obvious that this thing is convex. And it might not be a closed set. So that's already somehow weird going on. And the example, and I can give all the credit to Matthias that noticed all this stuff, is that this is the example that shows that the problem, the set is not closed. Why? Because if you take now epsilon goes to 0, going to 0, what you get is 1, 0, 1 on the left, and 1, 1, 0 on the right. And since this one is the same one as before, but this 1 minus epsilon became 1. And you see, if you compare these first two coordinates are the same, but now if you consider the second coordinates, this one is bigger than that one, and therefore this is like that, right? So now this guy is in lex, and this one is not. So you got something flipped, and this is exactly what this means, is that the limit of that sequence when epsilon goes to 0 is not in lex. So we found that it was interesting, and we continued thinking about it. And something kind of surprising happened, is that when you started considering and looking at this set more particularly, so first of all, and this is also something that was not clear at the beginning, was that this set was not only convex, but it was polyhedral. So it means that it was pretty much a polyhedron, like it has a bunch of linear inequalities defined in it, but some of the faces were open because it was not closed. And even better, you can show, and I'm not going to show, but I'm going to show the construction, that for any group, the number of facets of this polyhedron, of this semi-open polyhedron, is at most n squared. So the previous fundamental domains, like these ones over here, might have exponentially many facets, but this one have always at most n squared, which is already really good, right? And how do they look like? I can give you like a very, at first, a very simple example. And it's not very complicated in some sense. Okay, so first of all, you look at the first coordinate. One important thing then is that lex was not closed, so it cannot be a fundamental domain, but it's almost a fundamental domain. So the only thing you need to do is take the closure, and that's it. And it has at most n squared facets. And then you can find all the defining inequalities in a rather easy way in polynomial time and everything. Okay, so the first thing you do is you say, you know what? If I want a vector to be in my fundamental domain, the first coordinate should be bigger than a bunch of other ones. What does it mean? Like, it will be bigger than all of the other coordinates that are kind of reachable from the first one, right? Okay, so this notation, again, this is the group generated by, maybe I will say what this means. So I have two permutations there. This is a very simple example. I have sigma 1, which is a permutation, if I take the notation from before, 1 is sent to 2, 2 is sent to 1, and the rest is fixed. This is the first one over here. This is 1, 2. And the second one, this is a cycle of when you cycle these three guys. So you have something like that. And then 1 and 2 is fixed for the second one, and then 3 is sent to 4, 4 is sent to 5, and 5 is sent to 3. Right? Okay. So if I have this type of cycles, the group is relatively simple. And you see that 1 can reach to 2 and 2 can reach to 1, but nothing else. I cannot send 1 to 5 by any permutation. So they are like kind of disjoint. So the first thing I ask for is that the first coordinate is larger than the second one. And the second one is the one that I can reach from 1. Right? Okay. And then after that, that's kind of the first round if you want. After that, I say I will fix the first element because I already said that this guy has to be bigger than all of the other ones. And then I continue the same idea with the rest of the coordinates. And I do this in order because I'm lex. Right? Okay, now if I fix 1, I cannot move 2 anymore. And then I continue with 3. And then I say that x3 has to be bigger than x4 and x5, which are the other ones that I can reach if I even fix 1. Because I still have this permutation. So this is nice. Okay, so one thing that we discovered, like, say again?
What about 4 bigger than 5?
Yeah, but the point is that when you have to do that is you have to fix 1, 2, and 3. And see what you can permute after fixing those 3 guys. And if you fix 1, 2, and 3, you cannot move anything. Right? So that's why there's nothing else. You don't need it, yeah. You actually, it's not feasible to add them. Yes. Right. Okay, so what we found a couple of weeks ago, so we did a workshop on this type of things in Rancagua, organized with a few colleagues. And we noticed, we found out a kind of obscure a paper in a conference that we didn't know about, at least, that this type of inequalities were used in practice. Okay, and so which is kind of nice that people are actually using this. Although they usually did it just what they do in the literature, which is we just add inequalities and try what happens in practice, right? So now we're trying to, what this gives is a little bit more of a framework to study these things. Anyhow. Okay, so a little bit more formally what we, and I'm already finishing, what we do here is the following. We define a set of groups. So the first group is the original one. Then the second group, G1, is the group in which you fix the first coordinate. G2 is the group in which you fix the second coordinates among the ones in G1. So this means that you fix the first and the second coordinate. And then the third one, you fix the first 3 coordinates and so forth. Until you get Gn, which is the set in which you fix all coordinates and then you only get the identity, right? Okay, and how do you define then this lex G? Well, you say that x1 has to be bigger than xi for every I which is in the orbit of 1. And this means, I will actually define what this is. So of1 of G is all the j's in N such that I can reach J from I for some element in G1 in this case, or G0, sorry. So these are all the elements that I can reach from, sorry, my bad. So G, yeah. Yeah, J. Like that, yeah. So all the elements that I can reach from 1, which in the previous example, so I had 1, and I look at all the elements that I can reach from 1, which was 2, right? And then you look at the second one is very similar. You look at all the elements that you can reach now from 2, but from permutations in G1, because I now have to fix the first coordinate, and so forth. like that. And then this adds a bunch of inequalities, and those inequalities then define this fundamental domain. Okay, and we have a bunch of, we have a few other properties about this fundamental domain, but I don't want to talk about them right now. But I do want to say why I find this area so exciting, okay? And why I think that this might have like tons of consequences in the future research. The way I motivated these questions were about to understand why one way of breaking symmetries might be better than other ways of breaking symmetries. And you would like to measure this somehow, right? So one way of measuring things. And now let's go back to this very nice picture here. So one way of measuring how good this way of breaking symmetries is just to say, okay, here I have a number of facets, and here I have another number of facets, and you just count, right? And then hopefully the way of breaking symmetries is the one that gives you the less possible number of facets. That's clear. Yeah, but if you look at, if you know a little bit of polyhedral theory and integer programming theory, counting the number of facets is not a very good measure of how complicated that polytope is. And the reason, I have here a picture again, the reason is that if you want to describe a polytope, maybe you want to describe this polytope over here that has six inequalities, so 6 facets. You can always describe it as a projection of something that it lives in higher dimensions, right? So this is called the kind of an extension, an extended formulation of this guy over here. And what's the idea of doing that? This at the beginning sounds like maybe there's no point of doing this, but the thing is that you want to describe K as a projection of this guy over this higher dimensional thing Q. And here I have 6 inequalities, but here in the picture you see that you have, well, I don't know if you can understand it, but you have 5, right? Yeah, you have like this thing like this, you can think about it, it's like a triangle that you project, and you have like this, like you take the cross product with just a segment, and then you cut like on the sides. And you get this thing over here that has 1, 2, 3, 4, 5 inequalities. So you decrease the number of inequalities. And if you go into higher dimensions, the difference can be really big. So here you maybe have exponentially many inequalities, and here you have polynomially many inequalities, things like that. Okay, so now this is what I propose. Like, you have a way of breaking symmetries, or you have more than one way of breaking symmetries. And now what you want is to say, this way is better, or this way is better, if the extension complexity, so the minimum number of facets of an extended formulation, with one way of breaking inequalities, breaking symmetries gives you some number, and with another way gives you some other number. And then you can compare which one will give you a simpler polytope at the end of the day. It's not clear that there are actually differences or not. And this might say that there is no differences, and there's any way of breaking symmetries is always the same. Or maybe the extension complexity of the polytope without or with breaking symmetries is also the same. It's not clear. So in that case, maybe breaking symmetries is not useful at all. It's really unclear. But I think that this question is really fundamental, and we should really tackle it. So just to summarize. So the conclusion first is that you should always be aware of the symmetries of your problem. This is really important. Then the quality of these hierarchies that I just said before can be really affected by the presence of symmetries. But even, this is just one idea, but pretty much any algorithm you know of is affected by symmetries, and it's really important to be aware of them. So handling symmetries can significantly improve the quality of relaxations of your algorithms. And symmetries can be handled for general permutation groups efficiently. And the future challenges are how to characterize effective versus non-effective fundamental domains, whether we can avoid some pessimistic bounds from the extension complexity theory by breaking symmetries. It has to do with this last slide that I just presented. And what are the different combinatorial structures that, this is a bit more technical, like what type of structures of polytopes you can get from different fundamental domains. And one thing that is nice about it is that you need, in order for this to you need to develop a lot of the theories and techniques behind this, because there's very little around it. So we need to develop and transfer techniques from group theory in order to handle these questions. Yeah, that was mainly my talk. Thanks. Questions?
I have two related questions to what Peter said in the beginning. So, this description of the fundamental domain,
Yeah.
like these inequalities,
Yes.
this depends on your how do you detect what is the group of symmetries
Yes.
by a given polytope?
Yes.
Secondly, given a group, can you build algorithmically the generator? And
Yes.
is it enough?
Those are very good questions. And what I can tell you is that luckily those are pretty much completely solved. And the reason is that detecting or at least detecting the symmetries of our formulation, which might not be the symmetries of the whole problem, but to detect that, what you can do is that you take your formulation and there is some reductions that change, like to transform the symmetries of the formulation to a symmetries of a graph. And detecting the symmetries of a graph, that's the graph isomorphism problem. And that has been studied for 40 years. And there are like theoretical questions, algorithms for this. Like this is all this big result from Babai on graph isomorphism a few years ago. It says that you can do that in quasi-polynomial time, which, okay. Yeah. And there's a lot of algorithmic, there's a lot of algorithms that work really well in practice. So I was discussing this with Christopher Hoyne, which was one of the guys that we invited to this workshop a few weeks ago. And he implements this in Skip. Skip, you know, Skip is like Cplex, but for free. For poor people, yeah. Exactly. And they just use this thing out of the box in branch and bound algorithms and things like that. And he says that this is super fast, super fast. So either like in theory or in practice, that problem is likely solved. And what those algorithms give you is exactly a set of generators for the group of the formulation.
Can you go back to the formulation? We had a formulation where we had the problem, the optimization problem.
Yes.
So, I mean, the stuff that you discussed, if I understood,
Yeah.
has mostly to do with K, right?
Yeah,
So
exactly.
How come F doesn't
F.
play a role?
It does play a role or not, depending on how you want to deal with this. Like, if you want to look, if you're looking at relaxations, the fact that F, like the function is symmetric or not, it's not really relevant because you just look at the elements. Yeah, this is something that I didn't really explain too much. But you can always, yes, you can always do that, so you can get rid of that. But this changes the symmetries, right, of the problem. But the point is that, let's say, imagine that you have like a very symmetric problem or polytope, and then you want to optimize some function that can be linear or not. But this is symmetric, this is not symmetric. So this might break symmetries if you add it into your inequalities. You can still deal with this in the way we are thinking about it, in the following way. So let's say you have some fundamental domain, which is this guy, yeah? And then you want to solve this optimization problem. Maybe this polytope has tons of inequalities, facets, so it's kind of complicated. But let's say that you are given a point X, and you're using, let's say, the ellipsoid algorithm to solve it, or yeah, something like that, for example. So there, the point is that you want to separate X from your polytope, right? So you want to separate it. Okay, so one way of doing that is to say, okay, I will find the representative of the orbit of X. So I will find some G such that Gx is in the fundamental domain. I will solve my separation problem here, and then I will rotate it back, right? So the fact that C was symmetric or not was irrelevant, right? So you can just exploit the symmetries locally for a subset of the inequalities if you want, like that. No, no, no. I mean, that's when I was preparing this talk, I was thinking like, so,
Generated by this cyclic permutation, right?
or compositions of them. Yeah,
Composition of that.
yeah, yeah.
So that it's enough to think in terms of lengths.
But you might have other ways of breaking symmetries, right? So Lex is just one way. So Lex works for every group, but there might be others. It's kind of arbitrary. That was my point. Like the way of you defining like the objective function here.
Somehow
It's
intuitions that lengths exploit the full symmetries that you have.
actually it's not really, not really. And the fact that the set is not closed is giving you problems. It's because because then you will have in the boundary you will have issues. Because you will have points that are represented many times in the boundary.
Like the case that you showed with 101 and 110.
Yeah, that's one example, right? So it's not perfect. So I'm sure that this is not the best way to break symmetries always. I mean, it just works for every group, which is the nice thing. You don't think about it. You can just apply the set of inequalities and that's it. But
Question. What about if you just detect a subset of the symmetry?
that's always fine.
And
That always works. That's okay.
yeah, but I'm sure that it always does. But does it always helps to detect more
Yeah.
symmetries?
I mean, gives you in principle, it always gives you more inequalities. Yeah, that's for sure. That's not completely obvious, but it's always that.
Facets of that is not obvious.
The number of facets, I think is less obvious, but I would say that it does. It should be.
But you have inclusion of these sets, right? So,
Yeah.
so yes, so, if you take if you incorporate every symmetry, then you have like a tighter.
Yeah.
Tighter, but it may have more facets.
Yeah, but
So maybe closer.
right. But you never have more than n squared. That's the nice thing. And this n squared come from the fact that kind of the permutations that are involved here are generator. And yeah. And there can be at most n squared, yeah.
Also the algorithm, I think that you didn't mention that, but the algorithms used to produce these orbits and these stabilizers, those you can do that in
In polynomial time, yeah, everything we're doing here is in polytime. So we have to thank all the people doing computational group theory for many years to have a bunch of algorithms for us to use here. Yeah.
Just to get a sense of the impact of the, I don't know if you guys have tried some numerical tests to see what kind of
Yeah, so
scheduling problem. When you
we didn't do that though. So, but there has been people that has looked at this, and they work. They usually work, but not necessarily as good as some other methods. So the good thing about this is just you add the inequalities and forget about it. It works always, and it will give you some gain. How big is the gain will depend on the problem. Yeah, but yeah. I don't have the exact numbers in my head, but yeah, they do help. Yeah. But and what I really want to have a feeling for is like, is there any other objective function in which like way of breaking symmetry? Like to think about it this way, you can define any way of giving priorities for elements in an orbit and give you a different way of breaking symmetries. Like you could have like a quadratic function here, for example. And this should define a convex set and gives you also a different way of breaking symmetries, which is always a polytope for some reason. Yeah. And that's completely open and we should really think about it more.
We can think of something like x minus g of x belongs to a certain set.
Yeah, exactly. Exactly. As long as this thing gives you a convex set and then yeah. Exactly. Yeah. And you can define that in a very arbitrary way. Yeah. It's not clear whether you will get
What would be a good set?
yeah.
Beyond x.
Beyond legs and right. Because we know that linear things like these linear objectives don't really give you something manageable always. Yeah. Okay.
Any other questions? Thanks a lot again.
No.
Nice talk.
decía esto, ¿no? En tu Lex.
Yo creo que sí.